Hello, dear professors and every teacher. I'm Gao Peng from Beijing Institute of Technology. It's a great honor for me to take part in the 2025 ICACT conferences, and my paper is about how to surpass Cogging torque. My paper title is a Cogging torque suppression algorithm based on model predictive control. And my paper includes 4 parts. The first part is the concept of Cogging torque, and second part is about PI-based motion control strategy, and third part is about MPC and ESO-based motion control strategy. And last, I will give you a simulation validation. Okay, I will introduce the concept of the Cogging torque. So, what's the meaning of Cogging torque? So during the rotation of the rotor, the permanent magnet and the armature cogging structure inside the motor create a tangential force that interacts with each other. The torque generated by this force will attempt to align the permanent magnet poles of the PMSM with the cogging center line. In the event of a loss of power in the system, this tangential force remains, and the Cogging torque is the moment generated by this tangential force. For easy to understanding, a simple PMSM model is used to illustrate the distribution of Cogging torque over a cycle. The figure shows a schematic diagram of the Cogging torque distribution of the motor rotor rotation to produce a cycle. In a Cogging torque cycle, when the rotor is in a position where the Cogging torque magnet is zero, this position is the equilibrium position of the rotor, also known as the equilibrium point. So, how to surpass Cogging torque? I will give you some methods for surpassing Cogging torque. The Cogging torque of the motor can be surpassed by changing structural design and optimize control algorithms. In terms of structural design, this can involve modifying the stator structure, changing the rotor structure, and optimized wind design. However, for motors that have already been manufactured, employing structural optimization for surpass Cogging torque can significantly increase costs and may also compromise the motor's structure, reducing its operational performance. Therefore, optimize the motor's control algorithms can not only mitigate the effect of Cogging torque but also lower costs while preserving the motor's original performance characteristics. Now I will introduce the PI-based motion control strategy. So, as shown in the figure, the diagram illustrates the principles of the PMSM drive control system. The drive control system consists of 3 controllers: space vector pulse width modulation, and interval, a field-oriented control device, and PMSM. The 3 controllers include 1 speed loop controller and 2 current controllers, employing a traditional axis control loop structure. Among them, the current loop controllers include 2 PI controllers, which are used to stabilize the current tracking errors in DQ axis. But the PI-based motion control is the traditional control method, so I propose a new method. It's about MPC and ESO-based motion control strategy, and I will introduce. So what is MPC? MPC is model predictive control. The principle of model predictive control is straightforward and can meet the demands of multi-objective control, featuring a rapid dynamic response. It is particularly suitable for the nonlinear and multi-coupled complex systems of permanent magnet motors. Designing a speed loop controller based on model predictive control for the motor achieves better suppression of Cogging torque. Model predictive control can predict the future of outputs of the system based on current system information and compensate for model mismatches, noise, and disturbance occurring in each sampling period of the system. As shown in figure, this illustrates the principle of the MPC and ESO speed loop controller, where dt represents the total disturbance in the controller, including friction, external load disturbance, and in this paper, this disturbance caused by Cogging torque. And this part, I will introduce the simulation validation. An input value at motor load end is set to 1 Nm, simulating a distribution of Cogging torque. No additional load is introduced, simulating the motor under no load conditions. Through simulation analysis, the effectiveness of traditional PI control in suppressing Cogging torque is evaluated. To enhance comparability, an ESO is introduced to form a reference group for comparing the control effects of PI and PI plus ESO. Subsequently, the proposed Cogging torque suppression algorithm based on MPC and ESO is subjected to simulation analysis, comparing the control effects of MPC and MPC plus ESO. And the figure shows the position accuracy simulation results when the input command position is 118 degrees. Comparing the speed loop PI control and the speed loop PI ESO control methods. The figure A shows the position curve based on speed loop PI control when the commanded position is 118 degrees. It can be observed that when the rotor position converges to the commanded position, there is an overshoot of approximately 0.4 degree, and the oscillations occur during the convergence progress. In Fig B, it can be seen that the actual rotor position curve shows significant improvement compared to the PI control. However, there are still slight oscillations during this progress, with a maximum overshoot about 0.025 degree. Ultimately, the rotor position gradually approached the commanded position with a certain error. And these two figures show the position accuracy simulation results based speed loop MPC and speed loop MPC plus ESO when the commanded position is 118 degrees. From the Fig A, it can be observed that the Cogging torque suppression algorithm based on speed loop MPC has a significant suppressive effect on the Cogging torque generated by the driven motor, demonstrating a notable improvement compared to the previous simulation results based on traditional PI control. And from the Fig B, it can be seen that the balanced steady state of the entire control system has been further improved, resulting in a shorter time for the rotor to reach the specified position. According to the simulation results, after entering the balanced steady state, the position accuracy error of the rotor is nearly zero, indicating that the rotor has reached the commanded position accurately under ideal conditions without any error. This validates of the effectiveness of the proposed MPC and ESO control algorithm in suppressing Cogging torque. As shown in figure, the positioning accuracy speed simulation results based on speed loop MPC and speed loop MPC plus ESO are illustrated. In Fig A, there remains an issue where actual speed does not keep up with the command speed. The error between the actual speed and the command speed is quite large at the peak in the figure. And from B, it can be seen that Cogging torque suppression algorithm based on MPC plus ESO has improved the stability of the driven motor control system. The error between the actual speed and the command speed has significantly decreased compared to Fig A. Comparing these pictures, it can be seen that MPC and ESO control algorithm achieved better control over speed errors, leading to a more stable rotor during rotation. The comprehension of simulation results validates that effectiveness of the proposed MPC and ESO control algorithm in surpassing Cogging torque. And these pictures show the speed fluctuation suppression simulation results based on speed loop PI and speed loop PI plus ESO when the commanded speed input is 30 RPM. The figure A illustrates the speed curve when the specified speed is 13 RPM using a speed loop PI control method. It can be seen that actual speed fluctuates significantly, with an error of approximately 13 RPM between the actual speed and the commanded speed. The error is substantial, and there's also notable in the Cogging torque resulting in periodic speed ripples. The Fig B shows the speed curve when the specified speed is 13 RPM using a speed loop PI and ESO. With the introduction of the ESO, it is clear and the fluctuations in actual speed are reduced. Additionally, the period speed fluctuations caused by Cogging torque have been effectively surpassed. The error between the actual speed and the command speed is approximately 0.5 RPM. The suppression algorithm for Cogging torque still requires improvement. And this figure shows the speed fluctuation suppression simulation results based on speed loop MPC and speed loop MPC plus ESO when commanded speed is input 10 RPM. In Fig A, it can be observed that a Cogging torque suppression algorithm based on speed loop MPC significantly reduced the speed fluctuations caused by Cogging torque. Under ideal conditions, the amplitude of the speed fluctuations is approximately 10.6 RPM. After introducing the ESO, the periodic fluctuations caused by Cogging torque are notably surpassed, and ultimately the speed fluctuations is significantly reduced. And the last, I will introduce the conclusion of this paper. This paper addresses the issues of speed fluctuations caused by Cogging torque and the position accuracy of the motor when operating under low speed conditions. A control method utilizing speed loop MPC plus ESO is proposed to surpass the effects of the Cogging torque. The effectiveness of the proposed control algorithm in surpassing Cogging torque is validated through simulation experiments on positioning accuracy as speed ripple suppression on the simulation platform, providing a theoretical basis for subsequent experiments. Okay, that's all. Thank you for listening.